Hello everyone, this is Ty Everett, the original author of the CWI paper, Computing with Integrity. And that was 5 years ago now, so it's been a little while. And what I want to do is read the paper. And I just skimmed it briefly this morning and thought a little bit about it. And I wanted to make this video to talk about what stays the same, what has changed in the past 5 years in terms of getting this stuff done and getting it done right, where we are and where I want to go. So I'm going to start out by doing a little read through of the paper. I'll have a link obviously to all this stuff with this video, and we can start there. We'll go through it. I will give commentary as I read through it and describe kind of what CWI, Computing with Integrity, actually was, what it is now based on kind of my current understanding, and how it's going to change the world in the future. So we'll go through that as we read. And then I've got some slides, so where we can actually talk about what's changed in a little bit more detail and some strategies for the future to make sure that we act as good custodians of the CWI Computing with Integrity ecosystem. So without further ado, let's go ahead and get into it. I'm just going to switch to my window here where I have the paper up. And let's start with the title and abstract. So Computing with Integrity. There I am, 20 years old, 5 years ago. And actually I want to show you something. I just forgot about this. I have it right here. This is something I 3D printed in 2020. It's supposed to be the CWI seal with the little tetrahedron there in the center, hand-drawn in some 3D modeling program. And then I tried to convert my SVG file to an STL so I could 3D print it, and some of the text got warped, and I thought, oh, it's just a software, it's going to be fine. So this thing's existed for 5 years in 3D printed form. I just thought that was interesting. And yeah, I still have it, thankfully. I'm very fortunate to still have it now. Yeah, let's get into what CWI actually is. So the abstract of the paper reads, computing has long been subject to shortfalls in the areas of architectural cross-compatibility and information centralization. So basically that just means, we have problems where computers aren't very compatible, and when we use them, all of our stuff usually ends up under the centralized control of some company or organization that we have to trust a lot. And as I read, I might misread things, or I might have little areas where I'm just going to kind of paraphrase what it says, but I'll try to keep the message as close as I can as we're reading. So we define a new blockchain-based computing platform that standardizes user authentication and file sharing while providing verifiable integrity for application behavior and network services. So we're making something with a blockchain that lets apps and files work together in a better way that can be verified, meaning we don't have to trust centralized entities so much, and that's the goal, right? File systems can be created, updated, and shared with specific people or the entire world on a per folder or per file basis. Application developers can use existing technologies to build never before possible solutions for problems that have long plagued the existing model. Open-ended and extensible protocols and APIs provide for future expansion. And so basically that's just saying, when people have their files and their data, right now they might have them in their documents folder on their computer, but then, if their computer goes away, maybe it gets broken or something, well, then they got to probably upload it to some cloud platform, and then it's centralized. You got to trust that entity, and then you also got to make sure they don't go through all your stuff if you want to keep it private. So we could have a file system that could be distributed on a blockchain, meaning people could have access to all of that. And then you could keep it private. You could share it with some people who you want access to certain folders, but without giving them access, to everything. And then you could open up certain things publicly. So you have like a public folder that you're saying, to the entire world, like you can look in this folder and you can see what I have here. Maybe it's a project that I've worked on. And then they could make their own copy of it or something like that. And then, yeah, apps can be built using this operating system as well, or this kind of framework that we're talking about here, computing with integrity. And because of the nature of doing this in a decentralized way, in a distributed way on top of a blockchain, we allow a lot of things to happen that might not have been possible in the past. So let's get into it. This is just background stuff, and I'll kind of skim over a little bit of this, but basically, over the past few centuries, people have had a lot of ideas around computing. Things have advanced at a very quick pace. And it kind of all got started in terms of mechanically defined systems with Babbage, right? So Babbage kind of created a mechanical system. He was seen as the father of computing back in the day. And of course, there were others before and after, but that seems like a very significant moment when we kind of figured out, wait, we can automate the process of doing all of our computations and stuff like that. So yeah, I mean, now we have, VR and AI and all these crazy things, and it all got started when computers were used first to perform calculations. So, mobile devices you can buy for $30 or something, and they can do billions of computations per second. So that's just kind of laying the foundation for the world in which you currently live. However, users and businesses still struggle with the most basic of tasks. Things that should have been made trivial ages ago. So transferring files between computers that run different operating systems can be slow and cumbersome. So, publishing and sharing videos and documents is a complicated process. You'd have to set up your own servers and kind of do that yourself, unless you rely on centralized services to host all of that data for you. And sometimes the only solution involves uploading unencrypted copies of your files, because you don't know how to encrypt things yourself, obviously, to some cloud provider or a social network, only then just to download it again on another device or get it to your friend, because that's the only way you know how to communicate. So the big data-based advertising model creates a pretty bad incentive structure, and leads to building addictive and unhealthy experiences that sacrifice privacy in the name of convenience. And, native applications and programs lack true cross-device compatibility, while the only real standard for unified app development, which is the web, requires developers and users alike to entrust their data to cloud service providers. So basically, we have these apps on our Windows computer or our Android phone or our Linux server or our mobile phone running iOS, right, or our Mac from Apple. And yet, we can't necessarily use the same apps and systems across all of them unless we have a centralized backend server that connects it all together. And when you do that, you lose a lot of privacy and you create perverse incentives that corrupt the system of computation that we're trying to use, right? So CDNs, content delivery networks, and certificate authorities, we need to trust those people as well as trusting cloud service providers. And this is all bound to like the client server model, where your computer is just a client. It is something that talks to a server that allows an application to work. And the client server model means the clients have to trust the server, and the server is run by that company who has those bad incentives, and that's why we live in the world we live in today, essentially. So, when disruptive startups try to change this, they find themselves with a need to entrust their businesses to the very companies they're trying to replace. So if you go try to start a company that tries to build a better system for this type of thing, Well, until we had blockchain technology, the only way you could do it is by creating a centralized system that everybody would have to use. And so you kind of become the dragon in a bad way that you're trying to defeat. And so that's kind of the foundation of this paper, right? Systems that rely wholly on centralized service providers to operate are fundamentally susceptible to, manipulation and unprecedented degrees of control. And I go so far as to make kind of this foundational claim here. When they grow to encompass the entirety of the planet and to govern the affairs of every person on Earth, then these networks become unacceptable and even dangerous to the human condition. So that's kind of the foundation that we lay for this paper. In 2008, another paper, this one describing the first working version of a digital currency, was published. So there's the footnote for the Bitcoin white paper. For the first time, computers connected to a fully decentralized network were able to come to agreement about the sequence of events and to keep a ledger that no one can tamper with. And this phenomenon is known as the blockchain, and that's basically the basis for the integrity, right? Because the paper is called Computing with Integrity. So the blockchain is the basis for the integrity that this paper is describing. So that's the background, right? That is the background of computing with integrity, right? We start out by having an abstract and basically saying, here's what we're going to talk about. And then we say, here's the world, here is the stage that we're going to set for all of this. So, an introduction. Removing the need to trust centralized service providers and allowing developers to build applications that run in a deterministic way on client hardware independent of the architecture or underlying host system will allow standards to emerge that promote cross-device compatibility while protecting user privacy. Basically, that's saying that when we get together and make a standard that uses blockchain to allow for things to happen and allow for us to coordinate the state of our systems, and when we can do that in a way that works on whatever device you're using, whether it's an Android phone or a Windows computer or whatever, and have all your stuff in any device that you want, and when that's decentralized and secure, then we can do that in a way that has better incentives so that people can act more privately in the world. That's basically what that first paragraph is saying. A blockchain can be leveraged to store user data and track the state of a computational system so that users no longer need to trust a central server with their data. Anyone can download their profile into any device and see their files as they left them. And because the architecture for developing applications is independent of the host system, users can access and use the same operating system and set of apps across all of their devices. I think that's pretty self-explanatory. I mean, essentially we're saying here that when we use blockchain to do this stuff, then users don't need to trust servers anymore. And when you can put all of your data on any device, and when apps work cross-device, then you can access and use everything, essentially no matter what. So, and then we go on and we kind of provide more detail on this, and I think I've kind of covered a lot of this. Their wallpapers, contacts, and all other aspects of the system will remain constantly in sync. Files and messages they share with friends remain completely secure and are accessible only to those with authorization. All configurations, customizations, and settings are updated instantaneously across users' physical devices. And so the way we achieve that is by using blockchain to facilitate those updates and that coordination among those devices. But the end result is described here in the introduction. A standard API, a standard way to program apps for authentication, meaning knowing who people are and how to keep all that stuff secure. So standard API for authentication and for requesting permission to access personal information removes the need for, having passwords and managing a whole bunch of different accounts. So because all that happens in one place, in a system controlled by the user, we don't need tons and tons of different accounts. So certificate authorities are kind of like identity providers or something like that, that confirm who you are. Certificate authorities can verify the identities of users while providing privacy and transparency as they interact with one another on a more decentralized web. Meaning that when people interact, we have different ways of knowing who they are without the need to trust a single source of truth about who somebody is. Okay, so we start talking about technical stuff here, which is the bootstrapping and system access process. So we're talking about how can we get to this point, right? In the introduction, we laid out the vision for the future. Now we're going to talk about how do we actually get there. So to access this system, a user will need to be able to find their data on the blockchain, broadcast new transactions to mutate the state of the system, and securely access the cryptographic keys needed to view their files, sign messages, and perform other tasks. So essentially what we're saying here is when people get started, they need a way to find where they left off, and they need a way to do things where those things are kind of done in a coordinated way across all of their devices, and that way they don't get out of sync. In order that we may later arrive at this higher level functionality, we must first start by defining some lower level terms and concepts. In this document, we have terms meant to be interpreted as defined, and those are going to be capitalized, italics, and we'll use the Times New Roman font. And so setting the foundation here, and then we start to throw out some definitions for some technical concepts. And so I'll just read through this here without much comment until we get to ones that kind of have changed over time. So the system is the crypto system, virtual machine, APIs, file system, and suite of applications that are built in the ways outlined in this paper. The user is the actual human person who is using the system. They can do things as a human person, like typing a password, scanning their finger on a fingerprint sensor, clicking a button. They're not to be confused with the client. And the client is the software that the user interacts with as they actually use the system. So that's responsible for doing things like properly implementing this system and should enable its use. Any compatible client connecting to the system should attempt to deliver a similar, if not identical, experience for the user compared with other clients. So then we talk about secret server. So secret server is a server that is responsible for safeguarding the presentation key given to it by a client. So this establishes a mechanism for later verifying the identity of the user. So secret servers, they have this presentation key that was given to them by the client. And they're also responsible for establishing a mechanism for verifying the identity of the user who provided the key. And then upon successful verification, giving the presentation key back to the client that originally provided it. So when secret servers operate, they have different verification methods in order to basically, you go to a secret server, you say, hi, here I am, here's my presentation key. Please keep it and only give it to me again once I've confirmed, something about myself that I'm kind of putting together in this context. So, using SMS text message to verify a phone number, you could get a key back. Asking that a user, take a photo of themselves with, special instructions. That way we know it's the same person's face. You could also add government ID verification into that. Some combination of the above. Other options exist as well, right? So that's what a secret server does. And of course, I'm going to link to this, so I'm not going to kind of try to rehash everything here, but that's essentially, we'll go through some of these definitions, right? So to provide incentives that the users might choose their servers, secret server operators may offer to pay them a small amount of cryptocurrency during the initial bootstrap process. And that way, the user would be able to complete the initial bootstrap process and perhaps have enough to perform some tasks with their new system when they kind of get set up. And then to make money, secret server operators, might consider providing client software available for download, allowing offering services to the user so they could obtain, more blockchain assets. And I don't really like the term cryptocurrency anymore. 5 years ago, I did. So that's one of the things I would change. Is I would use the term like blockchain assets rather than cryptocurrency, just to be more correct. But allowing people to acquire these blockchain assets that they might need to use the system. Doing identity verification stuff, they could make money with that. They could operate a blockchain service provider or operate an image server. And these are two terms that I think I'm going to talk a lot about as we get to them. But essentially, I think that blockchain service providers are basically now, I would call those overlay hosts or overlay service providers. And then image servers, I think that's like UHRP, or the storage system called Universal Hash Resolution Protocol, has emerged as a tangible and concrete implementation of that. Now that we are in this world 5 years after this stuff was originally talked about. All right, so let's talk about the blockchain. It just basically has to be an immutable ledger, which the system uses to store and persist its state. The blockchain needs to provide reasonably consistent and liberal network rules, as well as inexpensive access for use of the ledger to store high volumes of transactions. I wouldn't say large amounts of data anymore. I would say high volumes of transactions. So I would also go so far as to say blockchain, for scalability purposes, would probably also need to have a UTXO-based model, meaning it has outputs instead of being like an account-based model, because I don't believe that would actually scale. So I would have added that. I would have definitely added that in there if I were going back. Blockchain service providers, again, businesses that sell or otherwise make blockchain data available in a highly performant manner in such a way that clients can effectively read and write data without performance issues or limitations. So yeah, overlay services, hosts, people who make money from running overlay services that actually expose various types of blockchain data. I think the implication here might have originally been it would have to be all blockchain data, but really it's only the specific subsets of data that particular people need, and not all blockchain service providers would need to have all blockchain data available. That's the only change I would really make there. Image servers. So again, I would make reference to the UHRP, or the Universal Hash Resolution Protocol, which is a way to store large data. And then people who host that data, they would be businesses that are paid to host, mountable images, which are part of like the file system we're going to talk about. And they would host those. They would serve them to anyone who pays the fees necessary to download them. That's still very true. Okay, so now we get into the first definition here, talking about things like what could be, in a file system. So think of like an ISO file or like a disk image file as a mountable image that we're talking about within the context of, building a file system on top of this technology. Yeah, I mean, we have essentially collections of files, folders, and other mountable image references, which would be arranged together into a directory structure. Mountable images could then be mounted at any point within either the file system or the domain system, and they might contain files and folders, references to other mountable images, as we said, static websites written in HTML, CSS, JavaScript, other languages, programs, apps, network services that leverage system APIs to deliver things like that. Dynamic protocols or methods for interacting with the blockchain, maybe using overlay services, I would add. Definitions for consensus rules that define new decentralized protocols for payments, communication, or governance. Random, basically smart contract things that could be defined in terms of code, which could then be executed by various people who might participate in those systems. Although I would actually say now that some of those types of rules, right? Rules and protocols might be more at the layer of overlay services on the blockchain itself, but you could certainly have a descriptor language, or like have a language that actually describes how those types of things might operate, and that's what's contemplated here. Databases and user data in use by members of any of the above's programs, apps, network services, protocols, etc. So you could have data that only certain people could access, or everybody could access in like a database format. An SQL thing could be in a Mountable Images. We go on to say executable programs that leverage system APIs in order to maybe even create other blockchains or some silly thing. I was talking about a lot of stuff 5 years ago, and I think that this is one of those things that might be a little bit beyond the scope of what a mountable image could contain. I mean, somebody could build an overlay that tries to, create a virtual copy of any other blockchain, but I wouldn't have gone so far if I were to write this today. I think that would be more building on top or having an application or something like that that uses the system versus putting that at the mountable image layer. I think mountable images is basically just a set of bits that you can host that represent some program or file or folder or directory structure, or an operating system that we're going to boot up, right? And that's like what we're going to talk about with the virtual machine and WebAssembly stuff. But once you have the ability to have mountable images, then you can do a lot. So operating systems intended for use within the system. And the system, again, that italics times New Roman syntax we're saying is kind of the computation environment that we're describing here. And then even source code repositories, package registries, I would go so far as to say as well, could be done in a similar way using that type of an overlay-based architecture. So that's my new approach on that. I think that's a little bit more aligned with where we are now. All right. Now we move on from mountable images to more foundational concepts and terms that we're going to use as building blocks to kind of define the architecture and the methods and the processes needed to achieve the end result that we set out at the very beginning in the introduction. So obviously we're going to think about some very foundational things. We have a password. So the user will have a password. Only one password for the entire system, including all of the applications that run on it, as long as those applications would leverage the system APIs for authentication. That means that as long as all the apps that use the system know how to use the system properly for authenticating, the user would only need one password in their whole life. And maybe you change that password or something every once in a while, like you do your phone passcode, but I don't think it would be having to do anything really more than that. The password should be secure enough to prevent brute force attacks, right? So combine it with a good password salt, etc. And here we are, password key. So in order to avoid the client, in order to avoid the direct use of the password in cryptographic operations, we need to run it through a key stretching function. So random password salt is generated wherever the password wherever to be changed. We're basically describing a way of doing this here. So a few 100,000 rounds of PBKDF2 should be sufficient to transform the password and its salt into a new password key. So basically what we're saying here is we need a way to make the password more secure, and we have a way to do that using cryptography and using key stretching functions specifically. Not terribly important here, but presentation key, that's important. It's another one of those auth factors that we're talking about. So we're building some foundational pieces here. A presentation key is a key that is generated by the client during the initial bootstrap process and subsequently shared with one or more secret servers during the initial bootstrap process. The key can act as a private, asymmetric encryption key to maybe receive some blockchain assets, for example, from like a faucet. So there could be a secret server that has a faucet, and that's how the user, when they create their new system with all their, their operating system and everything, all the apps they want to use within this context, they would use that faucet to actually create that that payment. They would receive that amount of blockchain assets, which they could then use to to help create the necessary transactions to facilitate the creation of their user profile, the installation of their operating system, the setting up of their file systems, and everything that they might want to have in their system. And so having some money available initially is kind of what we're saying here. That's why we're saying, during the initial bootstrap process, it could act as a private asymmetric cryptographic key, but that's not like a core part of what the presentation key actually is. So, and then it also acts, I think more importantly, it acts as a symmetric key just like the password key and the backup key, which is what we'll get to next. So we're setting up some keys and some authentication primitives here for kind of how this stuff might start to work and how we can start to tie these pieces together in order to create a cohesive system. So backup key is just a key that is generated by the client during the initial bootstrap process again and shown to the user in a human readable form. The user is asked to save the key in order to avoid losing access to their system in the future, right? And so those are the three kind of auth factors. You have your password, your presentation key, which is basically used with the secret server to get you some money when you get started, and then also you use that with the secret server in order to get logged in when you maybe have your. Again, we talked about how a secret server might verify certain things about you in order to give you your presentation key. So there's that stuff, your phone number, whatever, right? So we're thinking about your password, your phone number, and a backup key that you're asked to save when you kind of get started. And those are kind of the three things, right? And so now we're going to go through a set of steps and a set of things. I mean, we'll talk about some other things first, but at a high level, we're talking about having a password, your phone, and a backup key that you would save. And then you need at least 2 out of 3 of those in order to use the system, right? So the 2 out of 3 system is basically what we're talking about. So at a high, there's going to be some low-level cryptographic processes that we're talking about in the next few sections here. But at a high level, right, you need 2 out of 3 with your password, your phone, and your backup key. And if you have 2 out of 3, then you can log into the system, and there's account recovery in case you ever lose one of those things. And that's kind of the foundational architecture that allows for people to get into the system. But what does it mean to get into the system? And that's where we move on to the next thing, which is you have a main key, and the main key that you're using is called your primary key. So a primary key is a symmetric key. It's like a root key, I would say. It's a symmetric key that is used for cryptographic operations by various system components. And so basically what that means is once you're logged in, you have a private key, right? And that private key is, it's protected by your password, your backup key, and your presentation key, right? But once you're logged in, you get access to this kind of primary key, which is kind of the beginning of how we start to establish everything. And there are a few other keys here as well. I'm going to mention the privileged access key as well. The privileged access key is a symmetric key that is used by various system components for sensitive tasks. So you have your main everyday key, and then you have another key that is more sensitive. And that's basically what that is. So you have your privileged key and your primary key, right? And those are the 2 keys that are protected, right? So these 2 keys are protected by your password, right? Your presentation key and your backup key. And that's basically it, right? That's basically how users are able to establish themselves in the system without the need for a trusted third party. Because remember, we have the secret server, and the secret server might help store, a presentation key for a user, but you need at least 2 out of 3 in order to get access to the primary key or to the privileged access key, right? So that's the foundation. That's the foundation and the core of the authentication system that underpins the integrity of users and their credentials and the security that exists within the framework that we're describing here, within the capital S system, so to speak, according to the terms used by this paper, right? So we start by laying out these primitives, and now we'll move on. So we have the primary key pair and the privileged access key pair and the file system key trees and the file system read and write trees, and we go into some more details about that. And here's where I would definitely change a lot of this stuff, because basically we got better at cryptography, right? All of this is using a system called BIP32, an old system that is no longer kind of the best practice. We've moved on to a thing called BRC42 or BKDS. And so therefore, without going into too much detail yet, and I will still read the definitions of these other keys, but they're not used anymore. I'll kind of compare and contrast the old ideas with the new, which is one of the things I wanted to do in depth in this video. Essentially, what's going on here is we're wanting to make sure that we keep the system as simple as possible. And with a bunch of different key trees and using these different techniques, it wasn't the right way to go, and there were some problems. So over the past 5 years, we've learned a lot about better ways to architect the cryptography here to make this a more secure and resilient approach. So we have collapsed all of these other keys: the privileged access key pair, the primary key pair, the file system key trees, including the file system read tree and the file system write tree. All of that stuff is no longer foundational within the system, because they can all be derived using a thing called BKDS, or the BSV key derivation scheme, from the root primary key or the root privileged key where necessary. And that way we don't need so many different keys that are just used for so many different things at the base layer of the system. We will continue to be able to define things like file systems and other things like that on top, including the mountable image systems and the operating systems and the virtual machine and all of these capabilities for sharing files and facilitating, the execution of cross-device compatible operating systems using WebAssembly and doing all of that stuff at the base layer. But it doesn't need to use these separate keys, and we don't need to use BIP32. So without going into too much detail, basically, we don't need to use a BIP32 tree of keys in order to facilitate the operation of a file system and a folder or directory structure that achieves all of these goals within this context. And for that reason, this part of the paper that talks about BIP32 and file systems and the specific steps when we talk about later how we do things with a file in a folder and how you delete folders or files, how you grant access with read and write privileges to particular people, all of those tasks that leverage BIP32 as an underlying concept are no longer done in that way. So the cryptography for the 2 of 3 key system to facilitate user authentication with the password and the phone number and the backup key, all of that 2 of 3 stuff is all great. But now, rather than to use it to wrap a whole bunch of different keys, we only use that protect the primary key and the privileged access key. We don't need to do a different key pair for signing. We don't need to do different key pairs for the file system and all of that stuff. And so that's the main thing I wanted to say about those things. And I think at this point, I'm just going to move past these definitions. You can read them if you want in the original paper. But within a new system based on BKDS that does not need to use BIP32 anymore for its underlying cryptography, we can actually avoid the need for all of this complexity at this layer while still achieving the high-level functionality. Okay, let's move on. So I'm scrolling past all the stuff related to the file system. We described at a high level how it can work, and we'll continue to do that, right? I'm going to see if there's anything useful here. Basically it's saying knowledge of a given node constitutes the ability to decrypt the contents of that node, when also combined with knowledge of the public component of the corresponding file system write key, finding and decrypting the content of all child nodes also becomes possible. Basically what this is saying here within the context of the the file system keys is that when you have access, when somebody uses some cryptographic function to give you access to a particular file, then you can see that file and you can read that file and you can see if it's a folder, all of the child nodes, meaning all of the contained files and folders. And so that allows us to use these cryptographic primitives to give somebody access. Maybe it's read-only access or maybe it's read-write access. But the paper describes at a high level, and this maintains, we would continue to say this, but we would use different cryptographic primitives and steps to achieve it. This allows us to, once users can log into a system, then this ability to create a file system, the ability to share certain folders with other people, and the ability to coordinate state across your own devices privately, but also potentially across a collaborative environment where other people can edit files with you in real time. All of that emerges as a result of being able to protect that primary key and that privileged access key at the very beginning after you log in. So therefore, I'm going to breeze past the stuff related to specifics on how a file system works for the remainder of this video. Where it's mentioned in the paper, you can go and read it, but I think that we would use different steps and different primitives to achieve the same high-level goals and results. However, I will detail the authentication and recovery processes and kind of the initial bootstrap process, because that stuff remains the same and we continue to use that same 2 of 3 key system to this day. So the next important primitive I'm going to jump to here is called exclusive OR notation. So basically it's XOR. You have the ability to signify, so let's just read this, right? To signify a representation of 2 cryptographic keys which have been XORed together, the notation XOR key A, key B will be used, right? Then we define this primitive for the ability to encrypt and decrypt things. So when you have a symmetric key that you're going to use to encrypt and decrypt, then we just define this using AES256 GCM, which is a particular cryptographic primitive. So the specifics here are described in the paper, but at a high level, right? When data is symmetrically encrypted and decrypted, we stipulate, AES GCM operation as being implied using a 256-bit key. We also use a 256-bit initialization vector, and those get prepended to the beginning of the ciphertext. So when reference is made to ciphertext in the context of performing symmetric operations, inclusion of the prepended initialization vectors is implied. New and random initialization vectors should be generated 256 bits long for every symmetric encryption operation. Basically, we're using these cryptographic terms to describe some foundational capabilities, which is that when you have a secret key, you can encrypt something and you can keep your data private unless you have the same key which you could use to then decrypt it. And maybe you could share that key with somebody else using some higher level operation. So very low level there, but just making some definitions. Okay, here's another part I would definitely change about this paper. We do talk at a high level about broadcasting data to a blockchain in the form of transactions, and that remains consistent. To this day, we continue to broadcast data to the blockchain. However, we don't do it in the same way, and we don't treat the transactions the same way. So here we're talking about when data is broadcasted to the blockchain, it takes the form of an op return payload. Multiple push data operations are used. And basically we're saying a very specific format of transaction output scripts that contain particular data. However, this approach is no longer used. We instead use an output token-based approach that leverages the functionality of the blockchain and its tokenization, its intrinsic tokenization properties to facilitate the ability to, send data in a way that is going to be more scalable and updatable. And so we're just using some different underlying primitives. The high-level concept of sending transactions to the blockchain is also the same. However, we are not sending them to, just like the miners and then expecting the miners to give us access to all of our data for free. Again, we now have this concept of overlay networks that are specialized tracking services on top of the blockchain itself. And so because we have access to overlay services, we have the ability to create transactions that are sent to tracking systems that specialize in particular types of data. And so we can create transactions for things like managing user accounts or managing data on the file system. And we can send that to specialized tracking systems rather than sending them to everybody on the entire blockchain. And then we can query those overlays later for specialized, indexes or specialized like ways to keep track of all of that data. We can do it in a way that is much more scalable and economical than at first we contemplated within this original paper. So overlays are a much better way to do that rather than just treating the entire blockchain as like this deterministic, global state machine. We have specific views into that data, and that allows for much more scalability and specialization at various layers of the technology stack. So we say, the first part is a prefix for the system, so like a protocol prefix or something. The second is a message identifier for the type of data being broadcasted, and then the subsequent things are followed by 0 or more further push data payloads defined in accordance with the specifications for the message type being sent. Here we're being very, very specific, and sure, we can still have that type of prefix and that type of on-chain protocol or format, a structured way to send data onto the blockchain. But that structure and that data is going to use something a little bit different than op return payloads. So a new system that is relevant here is called PushDrop. And so 5 years later, reading this, I would say that we have different ways of using the blockchain that are more efficient, and you can have tokens that can have, fields that can be updated over time, and you can have different rules that apply in different contexts and different structures for the data. So we are very specific here, and I wouldn't have been as specific, or I would have talked about, a different system. I would have talked about PushDrop rather than using these op return payloads. But other than that, the high level operations, like I said, remain the same. So, looking back 5 years later, that's what's changed about, transaction data being broadcast to the blockchain. But let's move on. That's, we've learned a lot. What can I say? Let's talk about the initial bootstrap process. So this basically is what happens when the user registers for a new account on the system. The client, which is the software that implements the system once again, will do the following. And we define some very specific cryptographic steps and processes related to the 2 of 3 authentication system, the keys, how they're used, and how we kind of get set up. And most of this is actually still used today. We continue to use the 2 of 3 authentication system. And so let's go ahead and just step through it, right? Firstly, the client is going to generate a password salt and a password key based on the password that was entered by the user when they wanted to sign up, right? Generate a presentation key, generate a backup key, make sure to encourage the user to save it, right? So there's the 3 keys. We talked about the 2 of 3 system. And so what is the client doing here? It's setting up the foundation for that user to be able to access the system, for the user to be able to have identity and have assets as well. Because one of the things that wasn't contemplated originally in this paper was the idea that users can also use their identities in the system to sort of hold and own digital assets and tokens that relate to a vast number of different things. The user can also, trade those tokens and assets and money even with other people using micropayments, using smart contracts to engage in new forms of commerce. We didn't talk about that, but we did give the user these foundational authentication and identity factors, these 3 keys, the password key, the presentation key, and the backup key, which they can use to protect all of that data. So that's what the system does at the very, very beginning when the user is, in the initial bootstrap process. All right, so now we move to step 4. We are generating a primary key. I'm going to ignore primary key pair. We're not generating a primary key pair anymore. We're generating a privileged access key, right? So basically, we're making the primary key and the privileged key. And again, the cryptography has gotten simpler. Then on step 5, we're sending the presentation key to one or more secret servers, and we're completing any verification required by the user's chosen secret servers, right? So that can involve, like, entering your phone number and then verifying a code in order to have the secret servers sort of store that presentation key, and that way you could get back into your system later or on another device, right? So we're going through those processes. And now we have, the user saved their backup key, they know their password, and they've established that presentation key, those 3 auth factors, using one or more secret servers and using one or more, verification methods within those one or more secret servers to keep that presentation key safe. And then it's going to wait for the secret servers to send the faucet payment. So again, we're using the word cryptocurrency here, which I no longer like. I would use blockchain assets. So the client would then maybe wait for the secret servers to send those faucet payments to the user. So that way, at a high level, the user could, maybe the user could provide their own cryptocurrency, but the user is going to be able to broadcast the necessary transactions to kind of keep all of this registration information onto the blockchain, and that's what's going to happen in the later steps. So I'm going to jump around a little bit here, but basically, once we have all of these auth factors generated and saved, the user knows their password. The user has secret servers set up where the user could get back using that verification method, and the user saved their backup key, and they can use that to kind of get back into their account. And now we're going to do some more cryptographic steps here. But before we do that, I just want to jump to this footnote here. It says, it is possible for multiple secret servers to be used, each with their own presentation key slices. If you wanted to do something like, having multiple, so that way there's not trust given to one. Or you could have the same presentation key split up, or basically not split up, but you could have the same presentation key shared with multiple servers so that you wouldn't have to trust just one as well, right? So the slice could go, each to a different server, and then the user would have to go to each one by one, collect the slices, and once they have all the slices, then the user could they could assemble the final presentation key and then XOR all of those together or something like that using Samir, secret sharing algorithm, and it says, yeah, Shamir systems could also be used. So that's just a little footnote here talking about how multiple secret servers could work together to protect the presentation key or parts of it in different ways, and that is kind of contemplated here as one possibility. But within that context, either way, however it works, whether you just have one auth method with one secret server, or whether you have multiple with multiple secret servers, or however you set that up, you get a presentation key and you can use that as one of your 3 primary auth factors. That's kind of at a high level how the user registration process works within the system. So now we're going to move on, and again, I said there's some cryptographic steps here. So we generated the primary key, we generated the privileged key, and then we broadcast all of this data onto the blockchain. And here it talks about like broadcast onto the blockchain and then move on. In reality, what we're doing now, 5 years later, as we've got this set up, is we're actually broadcasting all of this stuff onto the blockchain at the end, after we do all the cryptography. It made a lot more sense in practice, and we went to actually go write the code for this to broadcast everything in one single transaction, which has a token in it that can be updated later in case you change, one of your auth factors, because you can do that, right? So just, bear in mind that as we define these steps here within the initial bootstrap process, all of the broadcasting happens at the end. And there are no, file system keys or anything like that. So step 8, right? Let's just move through this here. We're going to encrypt the primary key with the XOR of the password key and the presentation key, and then broadcast that to the blockchain, right? Then we're going to encrypt the primary key again with the XOR of the password key and the backup key. And then we're going to encrypt the primary key again with the presentation key and the backup key. So why are we doing this 3 times, right? We're encrypting the key 3 times in 3 different ways so that no matter which 2 of the 3 auth factors you have, there exists an encrypted copy of your primary key so that you can get back in and have your primary key again if you only have 2 out of those 3. So if you lose your password, you can use your backup key and your presentation key from your secret server in order to actually log back into your account. If you lose your secret server key, maybe you lost your phone or the secret server just went down or something like that, well then you can use your backup key and your password together to get back in and use your primary key again, right? So there's 3 ways that the primary key is encrypted, and that way we have 2 out of 3 possible ways to access the accounts within the system. Now we encrypt the, encrypt the primary key with XOR presentation key and backup key. Yeah, we said that already. Okay, step 11. We encrypt the privileged key with XOR of password key and primary key. That way, if you have your password and you already have your primary key, then you can enter your password and you can get your privileged key. And that way, you can have password protected privileged operations where it says, please enter your password or scan your fingerprint or whatever, as we'll get to later, to actually authenticate that. And then you can use your privileged key to do more sensitive operations. And then finally, in the case of an account recovery, we encrypt the privileged key once again with the presentation key and the backup key. So if you lose your password, well then you have the other 2. So you first use the other 2 to get your primary key, and then you use them once again to get your privileged key. So we're defining once again some cryptographic steps to actually create the record of this user and their identity on the blockchain so that they can facilitate access to all of their data. Step 13, we broadcast the public keys and we do all this stuff. Actually, none of that's really necessary anymore because, again, we're not using separate key rings for file systems and signing and all this stuff. It's all just unified into that one primary key and then one privileged key as the root keys for those various contexts, right? So we're talking about, encrypting the private key from the primary key pair with the primary key, and then we're encrypting all these other things. But, step 14, 15, 16, all that stuff is just not quite necessary, right? We're not using 2 different ones. So step 16, we are not generating 2 file system key tree root nodes, one read tree and one write tree. And we're not encrypting them with the primary key and broadcasting them to the blockchain anymore because it's simply not necessary. Once again, the cryptography has evolved in the past 5 years. We're not using BIP32 anymore. We instead have BKDS, and we've unified all of that together. And the final step, it says step 17, destroy the backup key, the password key, and the presentation key once the user logs in, once the initial bootstrap process has been completed. So this whole thing, zooming out at a high level, right? We're saying there is this initial bootstrap process by which the user establishes and asserts themselves with their identity and all of their authentication factors and the necessary steps and processes to save all of that and get it all set up and get onto the blockchain with some blockchain assets that you can use to actually create transactions and interact within the system and be able to log back in if you ever forget your password or anything like that, right? That's the initial bootstrap process at a high level. The client may now move any remaining funds from, the faucet, once we're all kind of established and set up, into, a wallet application. You can initialize, a file system, and we talked about how file systems are going to use different cryptographic primitives under the hood, but at a high level we can set up a file system now, right? Once we have those keys, then we basically have like a wallet, right? We basically have like a BSV wallet, and that way we can use these keys and the system to get to own assets, to use apps, to make file systems, to sign messages, to encrypt, to make transactions, to do all of that, because we have the cryptographic primitives and the necessary ownership of some blockchain assets to do all of that stuff. So after the initial bootstrap process is done, then the user would select and install and boot the chosen operating system that they want to use as described in a later section of the paper. So this is kind of where we are, I guess, in the sense of current times, right? We have wallets that can do that process, and we want to make sure those wallets are compatible with the later sections of this paper so that we can continue to build on top with integrity, right? So that we can actually run these computing platforms, these operating systems, these file systems, these network services, and these other things we're going to get to with integrity. And that's where we are, right? We have these primitives, this initial process described for how the user can get set up, and now we have these wallets. And what the client will do after it, sets up all this stuff and has a wallet and everything, what this paper will do, right? Now we're talking about an application, really, in the context of what a wallet would be, right? Now we have an application, and the application would then initialize the file system, boot the user's chosen operating system as described in the later section of the paper. Okay, so that's the initial bootstrap process for getting set up. And we have all of these primitives, all of these building blocks under the hood that come together to facilitate the operation of that system. Now let's move on. So signing on, right? What is the system's sign-on process? So suppose now we are in a situation where the user has already created their records, those things we just talked about, right? And now they're on a new device, or maybe they logged out and they want to log back in. How does that work? So let's walk through the processes, right? After the initial bootstrap process, when the user wishes to access the system, maybe on a new device or in a new context, the client, again that software, performs the following steps to bootstrap access to the system. How do we get back in? So step one, we contact the secret servers that the user has used for authentication and allow the user to verify their identity with the secret servers. So using whatever identity verification method was employed by that secret server, maybe again a phone number, using a government ID, anything else that we wanted to use, and then they would, through that process, obtain their presentation key, right? So that's step one. Now the user has the presentation key because they went through that process with their chosen secret servers. Step two, this says, scan the blockchain for the transactions broadcasted, that contain, that link back all this data. So getting, the password salt, encrypted copies of the primary and privileged access keys, etc. This says scan the blockchain for the transactions. The only thing I would change about this is rather than say scan the entire blockchain, I would say query an overlay service through a lookup provider, right? So we can use overlay services as a way to keep track of those tokens. And again, remember, we said that in the initial bootstrap process, in reality, we only broadcast one giant transaction that contains all of that information. And it's actually not that giant. It's only a few kilobytes in size. And then we can have an overlay network that keeps track of that type of transaction. And so in step two here, rather than scan the blockchain for the transactions broadcasted by this, we can actually just query an overlay lookup provider with maybe the hash of our presentation key and say, hey, I have a presentation key with a hash of this. Can you find me my data? Can you find me my UMP token, my user management protocol token that has all of these fields in it that allow me to access my password salt, my encrypted copies of my primary and privileged keys, etc. So first we go to a secret server and we authenticate with getting the presentation key set up. Then we scan the blockchain according to this paper. But in the new version, we actually just query an overlay lookup service. All right. Step three, how do we do this, right? Now we have access to those pieces of information. Step three, we use the password and the password salt to obtain the password key. So once again, we use PBKDF2 or some other key stretching function in the same way as we described earlier, using that primitive to actually get the password key, because the user enters their password at this point, and after they do the verification with the secret server, they enter their password, and then they actually get access to the password key. Then we XOR the password key and the presentation key, and we use the resulting XORed key thing to decrypt the primary key. So now we have our primary key, right? We're getting somewhere because we were actually able to log in by this point. Then we can use XOR primary key and password key if we want, to decrypt the privileged access key. And suddenly we have, again, those two primary keys that are used to facilitate all of our operations, because everything in the system depends on the primary key and the privileged access key. And we've just defined the process necessary, right? Go to the secret server, get your thing verified, look up your token from the overlay network, and then enter your password, and then decrypt everything. And now you have decrypted copies of your primary key and your privileged access key. And then we talk about some other things which might not be quite as correct. In step 6, we say use the primary key and the privileged access key to decrypt and obtain all other data. I guess that's technically correct. We can use that to, get on our file system, use other overlay networks to pull all that stuff down, boot up the operating system, etc. Yes, that's all still possible. I would have just used different, I wouldn't have used so many keys in this paper, When I was 20, I wrote this and I was like, gosh, this is really cool. And now I'm thinking, Ty, you made this really complicated. The cryptography could have been much simpler if only we didn't use, all these different keys. Step 7, use the file system read tree and the file system write tree to pull down and sync the file system from the image servers. So once again, at a high level, this is still correct. We would continue to, pull down the file system and do that, but we wouldn't use those separate keys. It would all be integrated into one. And then step 8, we initialize the virtual machine and boot up the operating system according to, the root bootloader, boot sector that was actually within the file system context. And so yes, that is still possible. And then suddenly we've defined the process for kind of system sign-on, right? So that's what the system sign-on process looks like. And largely, I would say it's about the same. And we're using, again, the same 2 of 3 system even now. So I would not change anything about this going back 5 years to actually facilitate access to the system in the same way using those same cryptographic primitives. It's only once we get access to the primary key and the privileged key that I would actually simplify it a lot and use different key derivation systems. Okay, so system recovery process. So at a high level, in case the user loses access to any of their different keys, then they may rely on the other versions of the encrypted primary and privileged access keys, which were broadcasted to the blockchain during the initial bootstrap process. So new versions of the affected key could then be, rebroadcasted. So this would comprise an update to the UMP token once the lost credential has been reset. However, since the XORed combinations only act as wrappers, the underlying keys themselves never need to change. And so what this means is that even if you change your password, even if you change your phone number, or you lose your backup key and you need to replace it, you can do all of that by just rewrapping those keys. And so once again, we talked about the 2 of 3 system and how that works. And so this definition here is basically setting up, it's defining the concept of how we can get back into the system in case one of our 3 primary auth factors gets compromised. Okay, let's move on. So proper use of privileged access keys. So here we're defining some procedures and methods that are used to ensure that actually everything remains protected. So the client may store and persist the primary key. However, the privileged access key should not be kept by the client. Since the primary key is known, and since XORing the primary key with the password key is used to wrap the privileged access key, we can simply ask the user for their password in order to decrypt the privileged access key whenever it's needed. Clients should prompt for the password or for biometric authentication often, basically generally every 5 minutes or so, when the privileged access key is continuously needed. And so essentially, we're saying that because the password and the primary key can be used together to decrypt the privileged access key, right? We don't need to store it and like keep it on disk anywhere in an unencrypted form. And then we obviously don't store the user password either, so that way they have to enter that or use some other biometric system to kind of unlock that. And that's what we get into next. So it's just defining some procedures for how we can make sure that even if, say the primary key was compromised somehow, someone got access to the user's, hard drive and was able to dump that key out, they still would need to brute force the password in order to get access to the privileged key, adding a layer of security. If the particular physical device on which the user is accessing the system supports it, then the client may use hardware-backed biometric authentication to protect a copy of the privileged access key with a device-specific key wrapper. Copies of the privileged access key encrypted with this device-specific wrapper should never be broadcasted to the blockchain and should only be stored in that specific device. When needed by the system, the user will use the biometric authentication method provided by the device to obtain access. So this describes how you can, maybe instead of entering the password every time, you could scan your fingerprint or something like that, and then you get access to your, you're authorizing whatever privileged or sensitive operation is happening using that high security key. And that's essentially how that works. That process remains exactly the same. I would not change anything about how that works. Now let's talk about file systems, operating systems, and image servers. So I'm gonna stop thinking about how the low-level details of file system implementation are incorrect. BIP32 would not be used here, but think about file systems at a high level. And now we'll just continue to read the rest of this paper because we've gone through the necessary cryptographic steps at this point to arrive at a situation where we can now use that underlying set of cryptographic primitives to achieve some really great things and get all the way back to where things were at the introduction. So let's go ahead and think about how this is going to work. Each user in the system will want a place to store their files, documents, applications, configurations, preferences, and other information. A file system should allow for permissioning, cross-device access, live data streaming, indexability, and highly performant operation. Cryptography should also ensure that data can only be accessed with authorization. For data stored within a blockchain, the file system should also be conscious about not replicating the same data more than necessary. So we're defining some high-level goals of the file system, and all of that is compatible with current understanding of where we want to go with this. To achieve this, we denote each node, which is a file, folder, or mountable image in the file system, as its own designated blockchain address. Here's where we go wrong, right? Because now we're not treating things as addresses and things like that within the BIP32 context or within that previous understanding of how blockchains work. We really need to treat each node as referencing back to the previous node and have a connected structure. And that's just different than how we're doing things. So the low-level stuff is wrong, the high-level stuff is still correct, and we can still achieve it. So we say, since BIP32 already provides a tree-like structure of addresses and private keys, we'll leverage this system to do our file system. And so we start with a root key, known as the file system right tree root key. And again, this is incorrect, but we can do the same thing using derived keys and protocol IDs and key IDs under BKDS from the root primary key and have like a file system protocol, which has a key that kind of can do the similar things as we're talking about here. There's not going to be like a blockchain address, so to speak, because everything's going to be like token based with outputs. It's not going to be off return payloads. It's going to be tokens that have particular data in various fields, and then that data gets spent forward when it gets updated. So we model the updates to the tokens as chains of spends within an overlay that tracks various file system operations and things like that. So I'm just going to kind of breeze past this here, right? But the root node is going to be at / obviously. That's still correct at a high level. And then to write to the file system, a transaction would be broadcasts. Maybe it could be signed with the file system key. where the data is going to be written, and then a history of the commits, again at a high level that's still correct, to a given file system node, which is a file or folder or mountable image, can be obtained simply by asking a blockchain service provider for the transactions coming from that address. And here's where once again, we're incorrect, right? We're not simply asking a blockchain service provider for transactions that come from an address. We are instead using a blockchain, we're using a file system overlay service on the blockchain, which tracks specifically transactions for particular parts of various file systems. We're using that overlay to look up transactions that are relevant and the latest state of actually various file system nodes, which are modeled by actually specific tokens. So you update a file system node by spending the current rendition of a token, and then you create a transaction that uses that node as input, and then it actually creates another node that is an updated version as an output in the same transaction. And that way, the history of a given file is modeled by the chain of spends for a given token that is tracked by a file system specific overlay network. And that's kind of how that would work in the modern context. All file system data is encrypted before it is broadcasted by the write keys, except public mountable images and public directories, which would be by their nature unencrypted. And then we have a second set of keys used for reading data from the file system, and that's known as the file system read tree. And at a high level, you can do something similar with BKDS. You can have one set of keys that say, I have the necessary authorization to spend the tokens and therefore facilitate updates. And then there's a read-only access. Maybe I can use these keys to decrypt the information about particular files, but I don't necessarily have the ability to spend those tokens at the same time and facilitate read-write access. So we have read-only and read-write. And even though the underlying cryptographic primitives and understandings are different, the high-level capabilities remain the same. So knowledge of a given node in the file system read tree constitutes the ability to read the data at that location because we can decrypt it. Knowledge of the private key necessary to spend the transaction output and then create a new one and follow the rules necessary to actually comply with the protocol and broadcast those transactions would give you the ability to mutate the state of that node, and then by appending commits or diffs or updates to that data within those corresponding tokens on the blockchain, so not addresses but tokens. That's kind of how that would work. So you would have the ability to essentially have read access and read-write access, and that's how you could do it. So that's how I would map those concepts over from the previous description, which leveraged BIP32 and blockchain addresses and a whole blockchain scanning system with a blockchain service provider. We now map those same concepts over so that they're now using overlay services, lookup services, specific tracking systems that track only blockchain-specific tokens for scalability and other purposes, enforcement of rules using an overlay network, and now we're using output-based tokenization with integrity based on the chain of spends to leverage the intrinsic tokenization properties of the blockchain to facilitate a tamper-evident log of changes made to a particular file, while still allowing those cryptographic properties around read-only access or read-write access by various different parties to a given node. And the constraints around that could even be enforced at the output script layer, where basically nobody can literally spend unless they follow the particular rules, meaning, you could say I need 3 out of 5 signatures to spend something. And I think we talk about that a little bit later. But now we just go on a little bit and we say generally 3 categories of file system operations are defined. So you have folder operations, which are denote a given node as a folder. You can name or rename a given folder, change permissions, or mark the folder as deleted, right? So if you do that, these are like various file system operations that are just generally done regardless. of whether it's on a blockchain, but we're defining this in a blockchain-based context, and you can do all of this stuff with outputs, with push-drop scripts, with tokenization. It might not even be push-drop. It might be some custom script that uses like a different protocol or mechanism, but it's not going to be op return, and it's not going to use blockchain addresses or BIP32 or blockchain scanning with indexers. Instead, it would use overlays and these new concepts which we have defined within the past 5 years. Now we'll talk about file operations. So operations that denote a given node as a file, name or rename the file, write data to the file, patch the file with a diff, change permissions, or mark it as deleted. File nodes are the only nodes which may not have any children. So that's reasonable. And then finally, we have mountable image operations. So this would use something like UHRP, or the Universal Hash Resolution Protocol, and the associated overlay, network, and data storage system. That has been implemented within the past 5 years, and we do have the ability to do that to build something like mountable images. And that way we don't store large amounts of data directly on chain. We can use hashes and an overlay to derive access to that data. And that's kind of what a mountable image is within this context. So operations that denote a given node as a mountable image, provide the hash of the mountable image to mount, provide contact information for image servers to download the image, provide an updated image hash, or mark the image as unmounted. So that way you can kind of mount images that contain directory structures and other things within any point of the file system, right? And we're kind of defining these file system operations here within this paper at a high level. During the initial bootstrap process, the client will normally mount a base operating system image of the user's choice at the root/file system directory. This constitutes the installation of that OS onto a user's system, right? And that way we have the ability to, use that operating system, and the mountable image can contain all of the necessary executable programs that use WebAssembly, as we'll talk about in a second. It will enable, a documents folder, having your wallpapers, having a runtime environment for your applications, and all of that stuff. The client must implement a virtual machine that runs the WebAssembly architecture. All operating systems and applications must compile to the architecture to avoid architectural incompatibilities. So remember at the very beginning of the paper we were saying all these different OSs out there, they're very incompatible. The architecture on which they execute is very incompatible. We should resolve that, and that's what we're doing by describing all of these primitives which we can then use to build up to that universal and cohesive solution. Clients should also broadcast an entry point. This is very important. They should broadcast an entry point into the file system, right? That the system, the virtual machine, can use to boot the installed OS. This startup program or bootloader is a WebAssembly binary serving as the initial entry point when executing the virtual machine. It is to be broadcasted as a special type of transaction to the /file system node address, it says. And so yeah, that's at a high level the same, right? The same problems exist. We're not using an address anymore, but yeah, you have a bootloader in WebAssembly that allows for this virtual machine to start executing this operating system and performing operations with this architecture. And that's how the user starts to jump into an operating system that of their choosing, right, using this unified architecture after they establish their identity, after they have the ability to have a wallet, after they have their primary and privileged access keys, and after the file system and all mountable images and other data is made available. So that's kind of how we make this transition from a user getting all set up to now that user is booting and executing an operating system within this virtual machine, and that virtual machine has the ability to do things like make transactions, obviously do file system operations, and all these other things. So that way, when the user makes a change within that virtual machine, then that change applies equally across all of their devices. And it allows that user to maintain access to all of their data, all of their apps, everything that they want to do across all of their devices. And that is the point of this paper. So now we'll move on, and we go on after we say that we have the ability to boot up the virtual machine in this way, right? Mountable images may be mounted at any node in the file system, including the root node, just like files and folders. Mountable images are not stored in the blockchain. Instead, when a client, again, a virtual machine execution environment client, right, the software that does all this stuff, which that client software, when a client creates a mountable image, it uploads the image to an image server. So again, UHRP server or UHRP host in current parlance, right? It uploads the file system image to an image server and pays a fee for the server to store the image for some length of time. That is exactly correct. We do not change anything about this even 5 years later. The client will then broadcast the hash of the image and contact information for any image servers that host the image. Image servers may charge a fee for downloading the image, payable transparently by the client in blockchain assets, right? So that way the BSV Satoshis can be paid directly to the UHRP server for facilitating their services. And yeah, that's all very true. That would work. We have this implemented. We have UHRP, and we can do this for mountable image servers and that whole system. Now, in terms of broadcasting the contact information for various image servers that host the image, this is an implementation detail of the UHRP protocol. That's not exactly how it works anymore. We don't rely on the client broadcasting that contact information. And we go into some more details about various things like that at various points in this paper. But generally speaking, the UHRP protocol and system, which is already well defined as of now, it was not well defined in 2020 when this was written. That UHRP system is handling that process. So let's move on. Some mountable images, such as operating systems, public network services, and downloadable application packages, so again, executable files can be part of mountable images if they use the WebAssembly architecture and are compatible with a virtual machine which the client executes. Some mountable images, like operating systems, public network services, and application packages, are left unencrypted. Anyone may download, mount, and freely use these mountable images as part of their own systems, as dependencies in their source code projects, as part of their websites and applications, as components for art or graphics or design projects, as components for new songs or movies, which are also public mountable images. And there's a footnote 2 here, right? And then image servers operators may set up arrangements to charge clients on a per download basis and compensate the mountable image publisher or author with a percentage of the revenue from their image downloads. Image authors can also operate their own image servers to avoid paying for hosting. For public images, the hash of the unencrypted mountable image is stored on the blockchain, right? And so that is completely true. All of this remains in effect. We have the ability to monetize and compensate people who upload images that are available for download when people download and use or benefit from the use of those images within their projects and make reference to the original, right, when you actually use it. So that's essentially what we're describing here. All of that remains unchanged. It is completely compatible with the UHRP system that has been developed. Let's move to footnote 2 because it's relevant here. Footnote 2 says, this allows for artists to use each other's work and make derivative works. For example, imagine a movie which is defined as a mountable image. If the movie uses a song, and if the movie's mountable image incorporates the song's mountable image into its own, anyone who downloads the movie will also need to download the song. The publisher of the song can delegate which servers the work is going to be hosted on, and can control the terms under which it may be distributed. For example, charging on a per download basis. Unauthorized hosting of copyrighted material in Mountable Images can later be proven by looking at the hash of the data on the blockchain. So because the blockchain keeps a hash of everything, we know that if you put unauthorized use of copyrighted material, we have proof, and we can actually compensate people for the fair value of that material later by knowing which content was used, how much, and how many people paid the fees necessary, how many people paid to get access to something they shouldn't have, right? So other mountable images, such as personal files, photographs, and documents, may be encrypted with file system keys associated with each mountable images file system node before being sent to the image server. In that case, the hash of the encrypted image data is stored on the blockchain, but not the hash of the plain text. When the client needs to change data that is stored in a file associated within a mountable image, maybe to make customizations, the diff between the images version and the modified version is broadcasted to the blockchain at the various location within the file system, a child of the mountable images mount point, where the file would have existed if the images files were to be incorporated into the file system tree. So basically what we're saying is you can have images that are mounted as part of your directory structures, but then you can make changes that deviate from what the image has so that you have your own version, and you can write those diffs to the file system at that location. All of that is still true. In addition to files and folders, mountable images can also incorporate other mountable images into their directory structures, and these child images can be mounted at any location within the parent image, including the image root. Multiple mountable images need not be mounted in the same directory at the same time, because that would create a conflict, right? So you can only have one mountable image as the root of a given directory at a given time. However, a second mountable image can be mounted in a directory after the first one is unmounted, right? So yeah, we kind of describe that process here, and then we give some examples. So as an example, if the user wishes to back up photographs into a folder called /backup/photos, the client will do the following. And then we describe some steps taken by the client in actually making this work. So create the backups folder. If the backups folder does not yet exist, then the client is going to look at the root level branches of the file system tree, right? And then we describe some very specific cryptographic steps and processes. We find the first unused branch in this example. We say branch number 35, and then we go ahead and, in this case, we say fund enough cryptocurrency into the address to broadcast a few transactions. It's definitely unnecessary to do this. So I would definitely change step C here. It's not necessary to fund the address because of the way that wallets have been architected and because of the improvements in wallet design and architecture over the past 5 years. We can definitely decouple the capacity to broadcast transactions from the actual system itself, so that it's not part of having the keys. It's just completely decoupled, and that also leads to greater privacy and security of funds and whatnot. So all of that should definitely be decoupled in practice, and that's something that we've definitely learned. So then it says the address would broadcast the transaction, and then the content for the op return payloads would be encrypted by the corresponding symmetric encryption keys. And again, we're not using op return, we're using a different system now, and it scales much better, so we wouldn't really use that. But at a high level, yeah, you encrypt things that go into these things if a particular operation is private, right? And then we go through some other steps. I'm not going to run through all of this. We create the backups folder, we create the photos folder within the backups folder, and we encrypt, pay, and upload. So the client will now allocate child nodes at the various endpoints, and then we go ahead and just do the encryption process. We use those newly allocated keys in order to kind of set up each of the file system nodes and put files into those places, and then we can either choose to concatenate into a mountable image blob, or we could actually do it directly on chain, depending on what the virtual machine execution environment wanted to do at that point, given the various things. We would pay the image servers to host whatever data needed to be put into a mountable image, and then we would authenticate, basically using an authentication system. And this is this point F here is actually very important, because we have much better and more standardized base layer authentication systems now. So the authentication process for facilitating communication between anybody who's dealing with BSV blockchain assets at this point is completely standardized. And so that's just like a very, very low level implementation detail. It's not even a concern anymore about this. And so is the payment process is all standardized. And so once we've paid, we can just upload the files and then use UHRP. If more than one image server is used, and in this case you could, then the client could, pay one server to send the file to another server for upload, and that way the client doesn't have to upload it more than once. The essential idea here is that we have the ability to have multiple image servers, and that way we're not subjecting ourselves to a single point of failure for any of the data that exists within our file system. And all of this is managed transparently by the client, by the way, which is that software that executes this virtual machine. Because as we'll get to, the virtual machine exists, and it has a few different interfaces that actually facilitate this process. So we go and say, suppose the user wants to delete this particular file. We actually describe the process here in detail. I'm going to skip past this because essentially, number one, you could check this out. It's fairly in depth and fairly incorrect in the sense of using these BIP32 root nodes. But at a high level, it is correct, and we allow the client, the virtual machine software, to make a decision about whether to re-image the directory and create a new image entirely, or whether just to write some diffs to the tracking system for the file system in order to facilitate that. That's an implementation detail of the client, which is actually hidden from the operating systems and the programs that are executed within the WebAssembly environment of the virtual machine. For public images, the same process will occur, except that the image data is not encrypted by any keys. The publisher of an image can still update the image by providing the server with a signed message from a key given to it at creation, or maybe we just use an authentication process that is already established within the BSV ecosystem. For example, the BRC 103 process, which is kind of current. And then we have another footnote here, which basically says it's possible to split a single key so that, for example, 3 of 5 signers will need to produce a valid signature and update a public mountable image, or you could even do that at the script level if these file system nodes are represented as tokens on the blockchain. You could have various constraints apply to the output scripts in that context. Image servers can set policies for hosting their images. This is all still very correct. The policies could entail, obviously, things like offering to host publicly mountable images for free, but requiring payment to host to download them. Depending on, maybe it's open source software or something like that, you could have different policies, whatever you wanted to do. Requiring payment in order to host mountable images and offering them for free downloads. That's an interesting thing. Allowing the public to crowdfund the hosting of popular mountable images, not hosting images they find offensive or controversial, or not hosting copyrighted material without permission. I think those last two are kind of, well, at least definitely the last one is very just implied, right? People aren't going to host that. But mountable image servers will enable that type of discretion within the system. Applications and system APIs are next. And so essentially what we're doing here is we've built ourselves all the way up into this new world where we have these applications that exist and can execute within this virtual machine. Applications and programs that run on the system, which is a virtual machine running the WebAssembly architecture, must compile down to WebAssembly. And this is to avoid architectural cross-compatibility issues. These applications and programs can leverage all of the APIs made available by the operating system, which the user has installed on the system at that time. Additionally, a few APIs are exposed at the virtual machine's kind of hardware level, or virtual, whoops, I just scrolled down far too much. Virtual API level, right? And we go further down and we actually describe some of these in more detail. But essentially, the virtual machine implements an ABI that allows for the invocation of various opcodes, the WebAssembly opcodes, etc. But there's going to be some higher level kind of hardware based, or not hardware based in the physical sense, but within the VM, the execution environment of the VM exposes a lot of different things. The ability to again read and write from the file system exposes the high level API for the file system to exist. All of this is still valid, right? We can still do all of this, and we intend to. This stuff has not been implemented yet, even 5 years after this paper has been written, but the primitives, the wallet, the keys, the identity, the authentication system, all of that stuff is in place. Developers can access these VM level APIs. Maybe there's like a region of VM memory that is sort of available for this or reserved for this, that can be invoked using particular system calls or like WASI or something like that. This is all not yet implemented, but can be done in practice once we get there. Developers can access these APIs the same way that they could access any hardware device by writing drivers so that the running operating system and user space programs can make use of them. So here we define some interfaces, and this is kind of the concluding part of the paper, right? We've successfully kind of brought ourselves into this world where we have this stuff available. We have the blockchain data interface, so basically it's a way to talk to overlays in a sense, right? We're basically talking to overlays in the new world, and then creating new transactions, right? So I list some old style operations here. This would not entail getting transactions for an address, getting balances for an address, getting addresses involved with a transaction, and it would include broadcasting a transaction. It would also include creating a transaction using the underlying wallet layer, the BRC 100 wallet layer of the BSV blockchain, which is kind of an integral component to the client, the virtual machine execution environment, right? We would proxy some calls. All the BRC 100 calls would be proxied down to that, in addition to the high-level file system APIs and all of that stuff, which is used to facilitate the execution of the WebAssembly environment. Since most blockchain service providers will likely charge a fee for access to the blockchain data, the client should transparently manage its relationships with overlay service hosts, essentially, and provide standard interfaces for the running operating system and user space programs to access blockchain data stored on those various overlay networks and within the file system. And that's what we get to next, is the file system interface. The file system interface allows virtual environment to perform tasks that relate to the file system. Operations might include reading a file from a given path, writing a file, create a directory, mount or unmount a mountable image at a given mount point, marking a file as deleted, list all files in a directory, mark a given directory as publicly readable or writable, causing the client to broadcast, basically write access or read access to the that particular file, using that file system level protocol, and granting read-write access to a given directory for a given user identified by their identity key, right? Causing the client to discover that user's public key, make shared secrets with that person, and then add those shared secrets as, add that user so that that shared secret could be used to, facilitate access to either read access or read-write access at various points in the file system. And then, explicitly request that a new mountable image, whether encrypted or public, be created for a given directory. Normally, mountable images would be managed transparently to the running operating system by the client, and would be encrypted by default, but this gives the user the ability to create and circulate specific mountable images as desired. And so those are the file system level APIs that would be made available within the WebAssembly execution environment of this virtual machine. The key material associated with the read and write file system trees should never be disclosed to the running operating system or to user space programs by the client. I think that applies actually at the low-level wallet layer with BRC 100. And then the client, does more stuff. It wraps things. It creates the WebAssembly environment. It interacts with overlays. It does these other things on top. But yeah, I mean, we never disclose the root, primary key or privileged access key. We only expose the ability to use those keys within the execution environment of this virtual machine. All file sharing and publication operations are to be implemented by the client via APIs, not by the running operating system. This reduces the attack surface and minimizes implementation complexity for operating system and driver vendors. Right? So we've defined now this ecosystem of operating systems that can start to emerge that use this client machine to facilitate this system of cross-device computation. And we have identity interface. So this is interesting. We actually implemented this within the context of BRC 100 for the wallet. And so we do have identity interface. And as we start to conclude here, we think about merging these interfaces together, right? Because there's the wallet interface, and then the client actually can be simpler because the wallet already does some of these things within BRC 100 within the BSV ecosystem. So the identity interface provides a way for the virtual environment to make use of the primary key, privileged key, for operations that might include encrypting a given piece of data, communicating securely with a counterparty. This would actually use type 42, or sorry, BKDS, versus just giving the shared secret to the running environment. We've improved our cryptography in the past 5 years to leverage BKDS for this purpose. So this identity interface is very, very baked in already to the BRC 100 wallet interface at the lower level. Sign a given message with a given key, or maybe get the public key, component of a given key. So we have the get public key method within BRC 100 at the wallet layer on the blockchain. The underlying cryptographic key material associated with the keys should never be disclosed to the running system or be accessible to any program running within the system. This allows the keys to be used for authentication and reduces the risk of unauthorized disclosure. All key material should be held and safeguarded by the client or even the lower level BRC 100 wallet that is used by the client. And we have a networking interface. This is the last thing, really, I think here. The networking interface is exposed to the VM as well, and this is implemented as the virtual hardware NIC device, the network interface controller in the VM, responsible for carrying out all functions of any other NIC, right? Additionally, this NIC will implement some extended functionality accessible to the system. So this is all very valid and whatnot. We're going to continue to do this. Essentially, message box server, or our BRC 33, is going to be part of this. And so the client would use a BRC 33 type system to facilitate the exchange of data over the NIC between parties directly. And then, yeah, we have IPv4 and IPv6 that can be done, move some packets across the wire, do things like that. But there's some additional functionality beyond just a normal NIC that would be made available within the virtual machine's execution environment within WebAssembly. So sending and receiving Ethernet frames and doing all of the functions of a traditional NIC. And then we add a mechanism for the running virtual operating system and user space programs to receive, to resolve domain names. First by attempting a traditional DNS lookup and then using the, decentralized domain system, root trust anchors configured by the client. So, we did also define an extension to the domain name system within this context. It didn't necessarily get implemented yet, and I don't know if it's still a good idea. That's something that is yet to be seen. But if it was implemented, then the NIC could abstract away that type of functionality as well, relegating it to the lower level, client layer, right, rather than the high level operating systems being executed. Establishing connectivity with the internet either by conventional means or by utilizing other clients and network bridges in a purely peer-to-peer mesh, right? And then transparently to the running system, the client should scan for and connect with other nearby clients and establish a purely peer-to-peer mesh. If one or more of these clients in the mesh has internet connectivity, then they could offer or sell their bandwidth to the other clients. And when internet connectivity is achieved in this way, then it should be transparent to the running operating system and user space programs. So, we continue to support that. I think that should be done. And 5 years later, nothing really at this level of the system has changed. I mean, we still have these ideas for the future, and we're still working to implement them, even 5 years later. So this interface should be implemented as the network card or NIC within the as a virtual hardware device for the VM, but would have some added features and functionality. Legacy drivers and software could still be able to use the NIC for access to the traditional internet within this operating system. When, for example, the client-to-client network obtains internet connectivity, it could be managed transparently to the system by the client. So the client is responsible for implementing peer-to-peer protocols that facilitate decentralized connectivity and might use things like Wi-Fi, Bluetooth, cellular systems, or any other mechanisms. Maybe even, Meshtastic or ham radio or other low-level peer-to-peer protocols available to whatever user's physical device is executing the operating system at that given time. And in that way, we could facilitate connectivity, right? We go on to talk about shared folders now. So users have long desired a standard, seamless, and interoperable way to easily and privately share files and collaborate on projects across the web. So building this functionality into machines at the virtual hardware level would allow for operating systems to make use of a standard API for the sharing of files and folders between users, right? So folders in the file system, which may contain other folders, files, and mountable images, can be shared with other users or published for the world. This would allow for private collaboration without the use of a central server. So sharing with other users is accomplished by the following simple process, and then we define some steps here. First, we get shared secrets between the relevant parties using the primary keys or the privileged key, depending. We then we encrypt the data at those various locations within the file system in such a way that we either grant read-only access, sharing only the keys necessary to decrypt the file system data, or we could grant read-write access to those various counterparties. It could be one or multiple, right? And that would mean you're sharing the read key, the keys necessary to do reads, but you're also sharing the keys necessary to spend and update and append data to those tokens in the file system, allowing for people to collaborate and have write-level access to various points within the file system. And then finally, you'd contact the other user's client using some means and then provide those keys in that way. And then suddenly you have the ability to collaborate, right? So to make the folder completely public, simply publish the keys necessary, unencrypted, right, to the blockchain at some location within, some public mountable image tracking overlay network, right? And that way, anyone could use the keys to read or maybe even write. That could be interesting. Having publicly writable, collaborative file system folders. I don't know how that would look, but definitely public read only, and then maybe even public read write for that part of the file system. You just publish the keys if you want it to be public, obviously. There's also now within BKDS we have counterparty anyone. So it's worth mentioning that as a way to facilitate public access. You just multiply 1 by G, and you use that public key to have access to the file system at that location. This functionality should be implemented as part of the file system interface, not by the operating system that runs in the virtual machine. This reduces complexity and attack surface for operating system vendors. High-level file system and sharing functionality should be exposed by the file system interface. So high level, right, not low level. And basically that allows for the OS to do things. And then it relegates all of the low level operations to the client so that the client can manage all of that stuff. The next section of the paper talks about domains and basically proposes an alternative DNS system. The current DNS system is fairly decentralized, so I don't see it too much of a reason to replace the entire thing anymore. I think 5 years ago I felt more strongly that DNS was flawed and we should replace it, but I've since understood a lot more about DNS, and so I don't necessarily believe that we need to replace the entire DNS system. I'm going to skip over this section of the paper, but it does describe updates to the DNS system. The only important thing here is that within the traditional DNS system, it's possible to use TXT records to point to the locations of mountable images that are stored within, UHRP essentially. And that way you can have a traditional domain name that has mountable image data associated with it in a backwards compatible way, or somewhat backwards compatible in the sense that you have a domain name still. But then you can resolve that mountable image using the processes described within this paper. So I'm not going to talk too much about the proposed DNS system. It's something that might or might not be interesting to some people. You can read through and maybe attempt an implementation. It would be interesting. I think people have tried something similar. We have the OpNS by David Case, and I think that was an interesting attempt as well. But I'm not convinced that we need to move away from the traditional DNS system at this time. I think that the people who are in charge of it haven't really demonstrated any dereliction of duty or something where we would need to replace that, and it is fairly decentralized in nature. So moving beyond that stuff, we talk about if we're going to integrate something like that, it could be done at the NIC layer within the client, so that virtual machine could resolve domains using that. We also mentioned that briefly earlier. All right. Moving on to network services. These are essentially overlay services at this point, right? I mean, yes, we have mountable images. The mountable images can contain executable WebAssembly binaries. Those binaries can facilitate programs that get run by the virtual machine within the operating system and within the constraints set by whatever operating system happens to be executing at that time, whatever user space that operating system makes available within the virtual machine's environment. And those binaries can facilitate, blockchain operations, can facilitate other things. That's operating system specific. In terms of binary formats for programs beyond just, WebAssembly as the architecture, and we can facilitate that within this context. But network services are essentially equivalent to overlay services within the new understanding, right? So over the past 5 years, we've developed the concept of overlay services that didn't exist before. And so we go on to say some more things about that here. But we talk about that. We talk about authentication as well. Again, we have BRC 103 now. So we talk about the ability to create digital signatures and authenticate people. We talk about the ability to exchange certificates and facilitate identity resolution. All of that now exists and is already implemented as part of the BRC 100 wallet interface. So there's no real need to to have specialized systems for that anymore. It's all already done as part of the wallet at this layer. There's that. We talk about identity verification and management with certificates. So at the user's request, clients can submit certificate signing requests to identity verification certificate authorities. The verification service can then verify the user's real-world identity and issue a certificate attesting to the given public key belonging to the user and having particular identity attributes verified. This is already implemented within BRC 31, BRC 52, BRC 100. We already did identity stuff as part of the wallet, so we just proxy those requests, the discover by calls and all that, down to the lower layer of the system. In the first case, we have the ability to have private certificates. Essentially, we're talking about the same thing as we've already implemented here. Certificates can have selectively revealable fields, and that is already implemented. So I'm going to move on. This is the final section, client-to-client connectivity. So again, we talked about the NIC already and how the NIC can expose some higher level functionality within the virtual machine than a normal NIC would. And we can do that kind of in a transparent or backwards compatible way. So since the client transparently operates a blockchain wallet that it uses to keep the system running, it can use various networking and peer-to-peer technologies to connect with other clients and to the internet. So that's extremely important for an IPv6 based world. For example, if client A is in reach of client B, and if client B is connected to the internet, then client A can contact client B and offer to pay for client B to relay internet traffic on its behalf. And then client B makes money while client A becomes able to connect to the internet or to any other clients in range of client B, right? So network bridges will emerge that attempt to earn a profit by making network access constantly available to all connected clients. And we go on further to say, beyond that, at the very end of the paper, onion routing and ring signatures will protect privacy. So that's essentially the vision of the system, and that's the end of the paper. We have two citations. I cited Faster Than Thought, and I cited the Bitcoin white paper. So that's the CWI paper 5 years later, and what I would have done differently. So it's also, I guess, a little bit of a progress update 5 years into the future about getting to this point where we now have all of these capabilities. And I think it's really good. I'm very excited to see kind of where things go from here. I think we've made significant progress, and I think the BRC 100 wallet is a significant step in the right direction. The final thing I want to do in this video is pull up some slides, and I just want to talk about a couple of things, where we are now and where we're going in the future to finish this work and get to the point where we have computing with integrity, because we are close. We have a lot of things to do and a lot of things that we need to be careful about so that we can get them right and so that we can be at a point where things work properly and where we can depend on all of this existing work. We have done significant work on the implementation of BRC 100 wallets as a standard, interoperable, and vendor-neutral solution for the BSV ecosystem. We have the ability to create transactions, facilitate identity and cryptography, including digital signatures, and we have those base layer things. We do not have file systems yet. We do not have a WebAssembly execution environment yet, and we do not have a network interface yet with a NIC, right, with peer-to-peer comms and whatnot. Those are still in the future, but we need to make sure that we can make most effective use possible of the foundational layers so that when it comes time to implement the client, in the capital C sense of the word as described by the paper, we have the right things, and so that we can actually get to a point where the client is able to do everything it needs to in a secure way and in a way that is not misaligned or would compromise user security at this critical juncture. And therefore, I'm going to pull up some slides and talk about kind of where we are. I'll summarize to conclude here, what all this is. So here's where we are now and where we're going. So So let's start with where we are now. We unified all the key trees, again, as I said at the beginning, into two sets, the primary and the privileged. So we're using BKDS or BRC 42, and it simplifies a lot of things compared to what was talked about in the original paper. There's no more separate signing key trees, and file system roots and equivalents can be done, essentially within the client, outside the BRC 100 wallet, but within the actual client, using BRC 42 primitives, protocol IDs, and key IDs rather than using BIP32 nodes. And we can do it much more securely and facilitate, access to the people that need it for various files, folders, mountable images, right? So we did unify and simplify the key trees. We also solved the base layer problems of the blockchain. So now we know what blockchain we're going to use, and we know how things are going to work, at least at some level, a lot more than we did 5 years ago. So overlays replace blockchain service providers. We mentioned that. Output-based tokenization enforces the order of events. So because one token spends the previous one, and that creates a chain of spends, we can use that as kind of a journal of particular histories of particular files, folders, or mountable images within the file system. Op return and scanning are replaced by PushDrop and lookup services. We talked about how that worked within the context when we were reading the paper. And then mountable images and high-level concepts are trivial to map over on top of the UHRP system. So that's essentially how that part works. And we're gonna continue to use tools like we've already built, foundational things like the UHRP as base layers to build on top. And then, finally, we simplified the identity and blockchain interfaces of the system. So again, capital S system there. The low-level BRC 100 wallet interface does identity. It already does cryptography and transactions all in one. And then wallets also allow the owning of assets and the tokens using outputs. And we can use scripts, we can use smart contracts and baskets. We can use all of these things, and we actually didn't contemplate that originally, right? So not only can we have a system that facilitates interoperability and cross-device access to all of our data, but we can also have a system that allows people to own things. And then, asset ownership and contracting are wallet-level additions not previously contemplated. So that's exactly what I just said. But that can be exposed within the VM to operating systems and the applications that use them in this future world, where we can actually now own assets, engage directly with peers with micropayments, do things like financial instruments and other exchanges, and all of that was added and brought to the table over the past 5 years by the BSV ecosystem and its blockchain that is capable of doing all of these things. And now we're going to be able to leverage all of these capabilities. That's where we are, and that's what we've learned over the past 5 years. We've simplified a lot of those interfaces, and we've made things foundationally better so that when the client, capital C client, is able to exist, we can easily use these wallets and the BSV ecosystem of wallets as an interoperable foundational layer on top of which to continue building the CWI system of computation. So let's talk about where we want to go. And I'm going to talk a little bit, about some cautions, some things I want to see, some strategy, some high-level things for the future, because we need to see this stuff. We need to ensure that there are interoperable wallets that have strong authentication within the base layer. We cannot have a fragmented base layer. We cannot have different people fighting about different ways to have authentication happen. Because if we do that, then we're not going to be able to focus on the application layer, and it's going to delay things. So let's see. Solving the sign-on process and associated problems at or below the wallet layer is extremely important. We talked about how that maps over onto BSV's wallet ecosystem, and that is already complete. But now we need to make sure that that ecosystem faithfully enables that type of authentication and does not allow the compromise of user-held assets. If I cannot depend on all BRC 100 compliant wallets to protect user private keys, if I cannot depend on the security of being able to to have all of the data associated with the wallet layer working properly, then I cannot build this system on top, because I need to worry about which specific BRC 100 wallet somebody is using. And to do that kills a lot of network effects, and it slows things down for the future, and it makes it much more difficult to execute on the higher layers of the system that are required. Ensuring that users and centralized, we need to ensure that servers, and centralized entities don't get hold of user keys. That is the key, right? Because if I don't know how that works, then I can't guarantee that when I build an OS on top of this, and when I create a system that users can use across devices, that the client is compromised, right? If that client is compromised and everything that user is doing, maybe it's fine on one device, but when they switch to another device that uses a different implementation of a low-level wallet, right, then there are problems. So we need to make sure that all of these wallets are secure enough to facilitate that, and that's why we need the 2 of 3 system within the BRC 100 ecosystem. So we need to allow the interoperable wallet to serve as a robust foundation on which to build things on top. That's kind of where we make sure things are going to work properly, and we need to know where we're going and keep our eyes on the prize when it comes to that stuff. Then we talk about building the file system, the VM execution environment, and the network interface controller on top. So once we have a BRC 100 ecosystem of interoperable wallets and applications and things like that, we have the blockchain and the overlay services and all of that stuff solved. We move on to actually implementing that file system and the execution environment, right? So once the interoperable vendor-neutral wallet layer is solved, then the client can be completed. An overlay for tracking file systems, the boot sectors for running WASM operating systems, and shared folders can be created. So BKDS and BRC42 primitives can be used to complete the private and public file system protocols that are used to coordinate and facilitate access within that context. The client's identity system exposed to running operating systems that use it can be proxied down to the BRC 100 discover by calls that are referenced within the wallet. The client network interface controller's peer-to-peer capabilities will use a message box server under the hood. So check out BRC33 and BRC34 for how that is going to work. We will use those primitives to implement that for the operating systems that utilize the system on top. And then in BRC 100 speak, essentially, the full client, the OS execution environment, the WASM virtual machine host, and all the system APIs, that's just an application in the BSV ecosystem that uses a BSV wallet, like any other application, right? So the CWI client execution environment for the virtual machine, etc., that is a BSV app. But it uses a BSV wallet, and that's why we need to make sure that BSV wallets are going to work properly, and we need to make sure that they create a strong guarantee around user authentication. As long as all BSV ecosystem wallets are secure and facilitate an interoperable sign-on and data sync process, CWI client can just build on top and exist within that ecosystem without any changes or incompatibilities. So making sure that wallets are aligned and able to stand up to the task and deliver will allow for the CWI ecosystem to extend the BSV ecosystem to completion, I would argue. But there are other BSV apps that will use the BRC 100 ecosystem that are not the CWI client, right? However, if the wallets in the BSV ecosystem are not able to make that type of client-only guarantee for the access to keys, well, It's difficult. Because then there needs to be an additional layer of tech, and I don't want that. I believe all BSV users deserve access to client-side access strictly to their keys. And I believe that identity is something that can be solved at that layer. And I think that's going to create a really great BSV ecosystem. But if wallets in the BSV space are not able to adopt that type of client-only access to keys and the cryptographic architecture that we described in the CWI paper within that base layer, it's going to make things difficult. So the next 5 years are going to be interesting. I believe that if we get the BSV ecosystem aligned within the next 2 years, if we get all these problems solved and we start to standardize a BRC 100 ecosystem of applications, then within the next 5 years we can complete the first CWI client before the 10-year anniversary of when this paper was written in 2020. We have made significant progress on building the foundational building blocks for this ecosystem. We will continue to execute on those foundational building blocks. We will continue to make sure that things are interoperable. We will not compromise on our core mission to make the internet work for people. And the CWI ecosystem is deserving of a base layer that lives up to all it can be. We've learned a lot, including the most significant contribution, micropayments and the ability to own digital assets, to engage directly, peer-to-peer, with micropayments and with smart contracts that facilitate exchange of value. And that's something that BSV has taught me. I hope that the next 5 years are going to be as fruitful as the last, and I look forward to continuing dialogue and engagement within this journey as I work to implement computing with integrity. I think we're going to go far, and I remain very optimistic about the future. There's been a lot that has changed. AI has shown its face in our world, and we have a lot to contend with there. But I think that AI will accelerate the process of development on this. I think that AI will also demand us to create systems that create more authenticity around what people create and exchange, right? We need systems that allow for real humans to identify themselves as authors, because otherwise you don't really know what's real anymore. You don't know what's AI generated and what's endorsed by a real human. And if we have computing with integrity, then we have the ability to solve that problem. And so I need BSV. I need the wallet ecosystem to live up to this. I think we can do it. I think it's going to solve a lot of global challenges that are ongoing, and I think we're going to be able to do it in time. I think we're going to be able to create something really good, and it's going to facilitate a future that we can be proud of, and that we can be inspired, and we can raise up the next generation of people to build things within the system, and we can do that on top of a solid foundation. So that's what I have to say. I want to thank everybody who has helped make this stuff possible, and I want to invite the next generation of builders as well, because we're going to need it. We're going to need it more than we've needed really anything, I think, in the sense of getting people to understand, getting people to contribute to this ecosystem, and getting it to the point where everybody has the ability to compute with integrity. Thank you.